Let me start with a brief reminder. That was the last slide that we discussed last week about the definition of quantum information. So we considered a setup very analogous to the classical case where we have two communication partners, Alice and Bob, and Alice wants to convey to Bob through a quantum channel a set of signal states. So these are pure quantum states that she created randomly. And through the quantum channel, she's only allowed to send qubits. And in a fashion completely analogous to the classical case, one defines the quantum information associated with this set of signal states and the pertinent probability distribution. One defines the minimum number of qubits that, on average, that Alice needs per signal state in order to convey that state to Bob. And I didn't give you the proof. There is a theorem behind that that's called Schumacher's theorem. Schumacher proved that this minimum number of qubits is given by the von Neumann entropy, and that's the formula at the bottom inside the box. It depends on the mixed state that you obtain when you mix all the signal states with the respective probability weights. Then you get a mixed state described by a statistical operator rho, and associated with that rho is the von Neumann entropy in this form minus trace of rho log rho. Like in the classical case, this is up to a multiplicative constant. This is precisely the entropy that you encounter in statistical mechanics in the quantum case, when you have a thermodynamic system described quantum mechanically, described with the density matrix or statistical operator rho, then this is precisely up to Boltzmann's constant, the formula for the entropy associated with that mixed state. So that's where we ended last time, and that shall be the starting point for a brief discussion of some key properties of this von Neumann entropy. At the top you see again the formula, and I would like to focus on three properties which parallel the corresponding properties of the classical entropy. The first property is completely analogous to the classical case. The von Neumann entropy is non-negative, and it is equal to 0 if and only if the state is pure. Classically, we had the property that was also non-negative, and it was 0 if and only if the outcome of the probability of the random experiment was certain. So one probability is equal to 1 and all the others are 0. And the quantum equivalent, the quantum counterpart of a random experiment whose outcome is certain, is a pure state. That's the maximum knowledge that you can have about the quantum system, is when you describe it with a pure state. Secondly, it is invariant under unitary transformations. So when you change the basis, you apply unitary transformation to your statistical operator, then this does not change the von Neumann entropy. It depends only on the spectrum, on the eigenvalues of the statistical operator, but not on the orientation of the basis. That's the analog of the permutation invariance that we had in the classical case. When you classically, when you relabel the outcomes of your experiment, then a permutation of the labels does not change the entropy, does not change your ignorance as to the outcome of the experiment. And the same here, when you rotate the basis, then this does not affect your knowledge or lack of knowledge about the outcome of the experiment. And then comes a first interesting deviation from the classical case. In the classical case, we had as the next property the additivity. The entropy associated with a combined random experiment is the sum of the entropy associated with one of them and the conditional entropy given the outcome of the first experiment of the second experiment, associated with the second experiment. In quantum theory, there exists no obvious analog of the conditional entropy that we had in the classical case. You can define a mathematical object formally. You can simply use that additivity that you have classically and solve for the conditional entropy and say the conditional entropy is the joint entropy minus the entropy of the first experiment gives you the conditional entropy of the second given the outcome of the first. And you can use that simply to formally define a conditional entropy also in the quantum case. Only that, in contrast to the classical case, this mathematical object that you define in this way is no longer guaranteed to be non-negative. So it's questionable whether it has any physical or other intuitive meaning. It's a quantity that can be negative under certain circumstances. So it's very questionable if you can still regard it as an information measure, because you would expect that information is always non-negative. So since there's no obvious analog of the conditional entropy, there's also no additivity in the same sense that you have classically. All you can say, and what is still valid, is the so-called subadditivity, namely that the joint entropy of two systems or of a composite state rho AB is at most the sum of the individual entropies. That still holds this inequality. And what also continues to hold is the condition for equality, namely you have equality if and only if the two systems are uncorrelated. If you have a product state, if rho AB is rho A tensor rho B, so it's a product state, then the entropy, then and only then the entropy is additive. So this part of additivity or subadditivity carries over from the classical case, but the part involving the conditional entropy does not. So this is one first deviation, and another and even more significant one is the following. Classically, the fact that the conditional entropy was never negative meant that the joint entropy of a combined experiment is never smaller than the entropy associated with just one of the two experiments. Yeah? So if you think of the additivity in the classical case, we had entropy of AB equals entropy of A plus conditional entropy of B given A. Now the fact that this conditional entropy classically is never negative means that the joint entropy is greater than or equal to the entropy of A, let's say, yeah, of one of the two experiments in isolation. That's what we had classically. Yeah, I write explicitly that this refers to the classical case. And due to the fact that this conditional entropy is no longer well defined and certainly not guaranteed to be non-negative in the quantum case, you no longer have this inequality. It is no longer guaranteed in the quantum case that the entropy of a joint system is greater than or equal to the entropy of a subsystem. Think of one particular example that we encountered many weeks ago when we talked about entanglement. We looked at the so-called Bell pairs. So these are two qubits in an entangled composite state. So the joint state, the composite state of the two qubits is a pure state. So the entropy associated with that composite state is zero. Yeah, the joint entropy vanishes. But then we looked at the reduced state of one of the qubits, and we found that the reduced state was a mixed state. Yeah, so it's one member of this Bell pair in isolation, considered in isolation, cannot be described by a pure state. It's in a mixed state. In fact, it was the totally mixed state. It was 1/2 times the unit operator. And this means that the entropy associated with this reduced state of an individual qubit is not zero. It's 1. Right? If we take all the logs here are base 2, are binary logs. So the von Neumann entropy associated with this reduced state is 1. So here we have a specific example where the joint entropy is 0 and the entropy of one constituent of one subsystem is 1, and therefore this classical inequality is violated. In fact, it's violated whenever you have an entangled composite state. In the quantum case, there exists only a weaker inequality, a weaker lower bound for the joint entropy, and this is the so-called Araki-Lieb inequality. The joint entropy is greater than or equal to the absolute value of the difference between the two individual entropies. We can quickly check whether this works out in our Bell pair example. Each individual member of the Bell pair is in the totally mixed state and has entropy, or with associated entropy, equal to 1. Yeah, and that's the same for both members of the Bell pair. So the difference of the entropies, S rho A minus S rho B, that's 1 minus 1. This difference is 0. So the right-hand side in the Araki-Lieb inequality is 0. And the left-hand side, the joint entropy of the entangled Bell state, that's also 0. Yeah, so it's satisfied. But that's all we have in the quantum case, this weaker lower bound. It has some interesting consequences. For example, if you have two totally different physical systems which are entangled with each other. So let's say you have a single photon entangled with an atom, let's say. So you have a composite system composed of an atom and a photon, and they are entangled. They are together. They are in an entangled pure state. Then the Araki-Lieb inequality tells you, well, the left-hand side is 0. The composite system is in a pure state. So the right-hand side must also be 0. And this means that the entropy associated with the photon must be equal to the entropy associated with the atom. So you have two totally different systems, but you know they are entangled. And then you can immediately say that the entropies of the two respective subsystems must be equal. It has another interesting consequence, which is known as the monogamy of entanglement. It's a result that you can also obtain in a different way, but the Araki-Lieb inequality affords a very elegant and quick way of understanding this kind of monogamy. Let me first show you the quick mathematical argument, and then let's talk about the name, why this is called monogamy. Imagine a composite system composed of three constituents, a tripartite system, three systems A, B, and C. And consider the entropy, so consider the composite state of all three systems described by the statistical operator rho ABC, and consider the entropy associated with that composite state. There are two inequalities that we can write. On the one side, we can say we have subadditivity, and subadditivity tells us that this joint entropy must be smaller than or at most equal to the sum of the entropies of two parts of this system, and let's split the system in one subsystem composed of A and B, and another system composed of only C. And then subadditivity from the previous page tells us that we must have this upper bound on the right hand side. On the left hand side, we can write a lower bound, which is given by the Araki-Lieb inequality. The joint entropy must be greater than or equal to the absolute value of the difference of these two entropies. So AB as one part and C as the other part. And then imagine the special situation where the two systems A and B are entangled. So A and B are in a pure entangled state. This means that the entropy associated with A and B vanishes. Rho AB is a pure state, so the associated entropy vanishes. Then insert this into these two inequalities at the top. Then you have on the left hand side only the entropy of C left. And on the right hand side you also have just the entropy of C left. So in fact, in that case, the entropy of the joint entropy of all three systems must be equal to the entropy of C. You can also write that as the entropy of AB, because that's 0, plus the entropy of C. And then we can exploit another property of the von Neumann entropy from the list on the previous page. That was the condition for equality for the subadditivity property. Now you have equality if and only if the composite system is in a product state. And here we have, as a consequence of this entanglement of A and B, we have the joint entropy of ABC being equal the entropy of AB plus the entropy of C. And this means that we must have a product state. This means that the state of ABC must be the tensor product of the state of AB with the state of C. When you have a product state, then the systems involved are not statistically correlated. They are completely uncorrelated. They're statistically independent. So what does this conclusion in the box tell us? It tells us that when we have three systems, whenever two of them are entangled, so in this case A and B, then the third one, C, cannot be correlated in any way with A and B. And this is where this name monogamy comes from. Entanglement is monogamous in the sense that only two systems can be entangled with each other, and it's impossible to add a third system which is also entangled with the first two or with one of them. Whenever two are entangled and you add a third system, this third system cannot be correlated in any way with the first two. So you cannot also have entanglement with the third one, not even classical correlations. And this very simple property of entanglement, the fact that it is monogamous, is in fact exploited in some protocols for cryptography. Because imagine that A and B are the legitimate communication partners, and they use, for their communication, they use entangled bell pairs. There exists a protocol. It's different from the one that we discussed. It's not the BB84 protocol, but it's a so-called EPR protocol that uses entangled qubit pairs, bell pairs. And an eavesdropper, that would be system C, an eavesdropper would have, in order to extract any information from the communication, would have to couple to these bell pairs. Would have to become correlated with the systems that in the possession of Alice and Bob. But this is impossible by the monogamy property. If the eavesdropper tries to establish a correlation with the quantum systems used by the legitimate communication partners, then inevitably this attempt will destroy the entanglement, because by monogamy it's impossible to do while maintaining the entanglement. So that's again something then that the legitimate communication partners can detect, and they can say, okay, our communication is not safe, and we abort the protocol and start afresh.